What we're going to do tonight is OSPF, Open Shortest Path First, with a multi-area environment. In ICND1, we looked at OSPF, and this is just another dynamic routing protocol. There's nothing complex about configuring any of these. Hopefully you figured out about configuring any of these dynamic routing protocols. It's just for EIGRP, it was router EIGRP, and then whatever the autonomous system number was, and then what networks you want to advertise. And the thing to keep in mind is that in that network statement, what you're telling the system is these are the networks that I want to enable this protocol on, and then I want it to advertise. If you have things like if you connect up, can't do anything, you know, without making a bad drawing. A couple of routers here, and we go to our ISP. We would have an interface here. That's where we want to turn the protocol off on that interface with a passive statement, so that it's not sending our whole, however big our network is, all of our configurations to the ISP. But other than that, typically it's just a matter of going into the protocol, router, whichever. We could do router RIP. We kind of hit a glancing blow on it. Router EIGRP, which was last time. Router OSPF, and then once we do the protocol, we just tell it which networks that you want to advertise. The easy way to figure out which of these networks you want is to use a show IP route. Once you do the show IP route, you'll get a listing of all the routes. What you want to do is advertise all the ones that have a C, the directly connected ones. That's a quick way of which ones you want to do is say, oh, which ones do I want, which ones do I not want. Do that. What I usually do is do router, OSPF, router, whatever, and then use the do show IP route. It'll give me a list of the networks, the ones that are C are directly connected. Those are the ones that you want to advertise. Those are the only ones that you can advertise, because that's the only one that the router actually really knows about. Everything else is something that somebody else told them, routing by rumor kind of deal. So OSPF, the multi-area, why we want to do it is for scalability, and we're going to have a picture here in a minute. If we had a lot of questions, and we had kind of had a little discussion last week about, hey, my home router is pretty smart. All I got to do is plug it in. Yes. So why is Cisco so stupid? Your home router will support, what, 20 to 25 workstations? Cisco will support 8, 9, 10,000. So you got to do some management, some configuration in it. 254, but depending, most of them, the wireless will support 25 or fewer. 4 ports. Well, yeah, but I could do those 4 ports, and then I could connect another switch and connect another switch and on down. Remember, we can do that because we don't really have a lot of the limitations if we do fast Ethernet with the switch port. So, yes, I understand what you're saying. Absolutely, wired 4 typically, wireless, yeah, maybe 20 of them. But in these guys, we can get thousands. We may get thousands, and the infrastructure. I'm just going to wait. We'll get to the picture instead of trying to do this here. And the OSPF routers have a database listing, and when you do the labs, they're going to have you to show the database. Have a database listing of the entire internetwork. EIGRP, in its tables, remember it had the entire topology in its topology table, so it's going to be a little bit faster on recovery. In OSPF, if something goes down, if the topology changes, it has to do a recalculation. EIGRP just simply looks into the topology table and says, oh, there's my backup route. Let me just use that one. So it's going to be a little faster. OSPF is the open protocol, and EIGRP is Cisco proprietary. Although I believe that Cisco's allowing other people to use it now. So each time a link goes up or down, the routers recalculate their database. So that's going to be a little bit slow to get to convergence. And convergence, when we converge it, everybody's got the same information. So convergence is where we want to be, that everything's there. So if we've got a really large network, let's say we've got a network of, 5, 6, 7, 800,000 routers. How long is it going to take for it to get all of that information to recalculate everything once something changes in the topology. It's going to take a while. And it's going to take a lot of CPU reps. It's going to take processing power to do that also. So scalability, the OSPF, the single area, the one that we did, puts all the routers in one area. And so the routers flood the entire internet network with LSA, link state announcements is what an LSA is, telling it about all this stuff with each topology change. So topology change, something changes. And things go up and down. Routers go up and down. That's why on the internet is basically kind of sort of like a great big huge rip, but it doesn't try to do convergence very quickly. It's also very slow in doing that, because how many routers on the internet do you think go up or down on a single day? So you don't want those topology changes to initiate immediate change, whereas in our networks, OSPF networks, we want that to happen. Given your choice, EIGRP is by far the best protocol, but again, it is Cisco proprietary. So if we divide it into multi-area OSPF, then we can resolve those issues. So what we're going to do is take these things and put them in different areas, so that this area, if we got 3 or 4 or 5 or 10 routers, they talk to each other, and these over here talk to each other. At some point, we got to have a router that has interfaces in both areas. And when it does that, it is the one that then communicates with the other areas. These are the area border routers, and we'll get to some of those definitions in a minute. But area border router sort of summarizes everything. It does summarize everything. And that's the only place that summary takes place in OSPF. EIGRP, the individual routers do auto summarization, which when we did the labs was it kind of causes you some problems, because we used 10 networks in that one. And then each of them summarized and said, I have all the 10 networks, when they really didn't. So the route tables didn't work until we tell it to do a no auto summary in EIGRP. What that means is all of this subnetting stuff that we had and supernetting, you really need to set these things up in an orderly progression so that you've got networks here that can be easily summarized when you do that. Because the summary routes is what it actually passes. If we had like 192, 168, I don't know, we can have several of them with a different subnet mask here, and we had a 192. It would do 192.169, and we could use a 255.255 for the summaries on these things. We could use all the 192.169 addresses over here. So what this router would say, hey, you want to get to a 192.169, go to this guy. And then it will have the routes to all the individual routers. Does that make sense? That kind of maybe help a little bit with summary. So we do 192.168s here and 192.169s here, and then we'd have a 255.255 subnet mask. That's what summarization kind of is. So the shortest path first, the scalability in the single area, area 0, we have a whole bunch, and this is supposed to represent a whole bunch of routers. They're all communicating, and they're actually all communicating with each other to share this information, to share the database that we want to do that. If we move to a multi-area, then this is more area 0. All the routers flood the network with link state information, which we said before, LSA, link state announcements. We're also going to have some other things like requests and updates when we do these things. But they're all in the same area, so they're all talking to each other. A lot of traffic in a single area. If we have multiple areas, they flood the network only within their own area. So area 1 talks to area 1, area 2 to area 2. And area 0 here, which is going to be called a backbone network, doesn't have anything else in it, but we could have others, and they would only talk to them. We have the ones here between that have interfaces in 2 areas. These are going to be the border routers, and they're the ones that are going to communicate across the areas. And this kind of all happens automatically. We have to have an area 0. If we have a single area, it has to be area 0. And all of the other areas must connect to area 0, the backbone. So if we had other ones up here, we could put routers in it. We could have multiple areas connecting to this, but they need to connect to area 0, at least one interface. in a border router in each of the areas other than 0 need to connect to area 0. Adjacency requirements and adjacency are two routers that are talking to each other. They're going to be connected here. We use the hello protocol, and I think I've got an image here that kind of gives it. We got a hello. Hello, are you there? And then it answers back with an acknowledgement, yes, I'm here. And then we can form an adjacency. And these hello messages are going to happen, I think, here, and I have a slide, so don't hold me to this, but I think it's every 5 seconds. Sounds like a lot of traffic, and it kind of is, although this, remember, is not broadcast, but it's going to be multicast. So it's not as bad as broadcast. It sends it to the multicast address, but every 5 seconds it's going to send these things, and then we're going to have how long are we going to wait, and it's usually about 4 times, and actually I think that in the configurations on the ones that we have, it's going to be 40 seconds. So it'll wait for 40 seconds before it says, hey, that router's not working anymore. So when we can do these things. So the database synchronization, this says 3 packets. I added one because I thought it should be there. We have the database description packets, which start the thing out. We have the link state advertisement, and that's kind of in the link state advertisement. And then we have link state requests and link state updates. If something happens, a router can ask to be updated. If something happens to the topology on a router, it should announce that. And the LSU, the link state update, obviously is in response to a request. To form an adjacency, the area IDs and the area number is part of the configuration with the network command. So you have to do that. So the area IDs have to be the same. It says subnet, and you read some, it says the subnet mask has to be the same. They have to be able to talk to each other, obviously. The hello and the dead timers, the hello is how often the hellos are sent. Hello is how often. And the dead timer is how long am I going to wait before I declare that route or that router dead. And it's usually 4 times. It's typically going to be 4 times the hello. And then if you have authentication, it has to be the same. And that's just like, you know that. You have to be authentication. You have to have the same key in order to do that. Authentication is not a requirement. You can have it. You don't have to have it. So we can do these things. These are the 3 types, the link state messages. The link state advertisement are included in the database description packets, and that's why there were only 3 over there, but I thought it was important to say, hey, we have this other thing really. Include the link state type, the address of the advertising router, cost of the link, and the sequence number when we do these things. The link state request is when a slave router receives a DDP, a database description packet. It sends an LSA link state LSA acknowledgement packet. Then it compares the information that it got with the information that it has, and it may send an update. It sends an LSR to the master router in order to get updated. And the link state update is simply the update message in response to the LSR, to the link state request. This is kind of a step-by-step to form an adjacency, and I said an acknowledgement. They've sent it hello, hello. So this is going to be the initial. The X start is in here. Is the DD is the database description messages when we go through this thing. You notice there are several of those, and each of these have sequence numbers so that it keeps them going on. And then we'll go into loading state, and once we get into loading state, we get full, and when we're full, we're actually ready to exchange information. Remember, this is for the OSPF protocol, so this is what happens in order for these guys to say, hey, let's talk OSPF instead of let's talk English, or let's talk Chinese, or let's talk EIGRP, or let's talk RIP. We're going to talk OSPF. So the categories of multi-area components, we have backbone routers, they're in the backbone area. Internal routers, they're in any other area. And then we have area border routers, those are the ones with the interface in 2 areas. And then the autonomous system boundary routers, that's a mouthful. Those are the ones that are probably going to your ISP. if you had one that went from OSPF, if we went from OSPF to EIGRP, that would be IGRP. That would be an autonomous system boundary router if we go out of the OSPF areas. Dijkstra, that's a word that you may want to know, is used to calculate the shortest path first and place the routes in the table. And that's the only thing I ever knew that you had to know is Dijkstra. That's the name of the algorithm that calculates these things. This is a picture of the same thing, the router roles. What we have here, backbone router here is in area 0. The area system border router goes to a different autonomous system, which would be not OSPF. We could say not OSPF here maybe. And then we have the area border routers. Again, we have an interface in different areas. An internal router is going to be in a router other than area 0. So I think that takes care of all of those terms in it that we talked about. Backbone area, backbone routers, internal routers, any other area when we do these things. The link state announcement or advertisement, also known as the router link advertisement or the link state advertisement, sent by every router to all of the routers in the same area. A router connected to multiple areas like these guys will send separate type 1 link state type 1 LSAs in each area so that they get the information from each area. And this again is these are the guys that are going to communicate area to area. Now, these local routers down here don't share information with any other local routers with anybody in any of the other areas. The type 2 statements generated by the designated routers, the DRs, for all routers in an area. A DR is elected in a multi-access. And the DR, we're going to have a DR and a BDR. And these guys are elected, and they're elected based on the highest IP address of an interface, of a loopback address. These are terms that you heard before, or we can put in a router ID. So the designated router is the one that everybody sends their information to the designated router. It then sends those updates to all the other routers. But these are only in multi-access, which means Ethernet, basically. If we have point-to-point, they won't be there. And when you do the labs, some of them are going to be hooked to switches, Ethernet kind of things. Those are multi-access. They'll have a DR and a BDR. The ones that are on the serial interfaces won't have that when you get to convergence. So we have a DR and a BDR. BDR is if the DR goes down, the BDR automatically takes over these things. So they're elected based on IP or router ID. And the router ID, so that means that you can basically force one of them to get elected, so we can fix the election there if we want to. Summary link state advertisements these are generated by the border routers to all the external routers, and it advertises the interlink routers, contains the IP, the RID, the router ID of the area border router when we do these things. And then the type 4 are generated by border routers to inform the rest of OSPF how to get to an autonomous system border router. These are things like you can do this. These are type 4. They may send a default gateway announcement to a downstream system so that you don't have to put that default gateway into all of them. It will actually send it for you. And external announcements are generated for the external network advertised by the ASBR. And the external network is going to be something out there. The external network could be an EIGRP network, could be a RIP network. So an external, something other than OSPF is external. And this is an image here again of the type 1. The type 1s, we're talking within our own area. Type 2, type 1 and type 2 within our own area. Type 3 are the summary messages are from the area border routers here. The ASBR, the type 4, the ASBR summary this is going this direction. And then the type 5, the autonomous system link state algorithm go in these things. So the hello packets, I was wrong. I was wrong about one and right about the other one. It's every 10 seconds you're going to send the hello messages. So that means that the dead is what I remembered is 40 seconds. So what this says is every 10 seconds we're going to send a hello message. Yeah, and we'll wait 4 times. And you can configure these times. So if you don't get a response from that router within 40 seconds, everybody does the recalculation business. So the hello packet's going to be the router IP, the router ID of this thing, the hello and the dead interval, neighbors, its neighbors, the area ID, the router priority, the designated router IP, and the backup designated. And then if you have authentication, it's going to be there. So the hello message really has a lot of information in it that these guys want. The neighbor states is used upon initialization. The neighbor states is probably a bad, not good title here, but it uses multicast. 224.0.0.5 is what it's going to do. After the relationship is established, they synchronize their link state databases so that everybody's got the same information. But again, the only thing that a router advertises is what it knows about, and what it knows about is what is directly connected. There are a number of states, and if you want to do it when you do the labs, save the configuration, do a reload, and then show the database and watch it go up. It'll go from down to what's called a two-way, and then it'll eventually actually X-start. It goes through a whole bunch of different processes, how far along it is. What we want to get to is full state, which means that we have the databases are all in agreement with each other. So the relationships down to temp, init, initialization, two-way, X start, exchange, loading, and full. This is something that kind of sort of you probably want to be familiar with the terms for the Cisco situation. And then these are from the book itself. I think these are right out of the book. So the hello here, 224.0.0.5. Important to remember multicast M.5 because there are other multicast protocols they use different addresses. And what the .5 is telling it that, hey, I'm sending this out. This really is a hello, an OSPF hello message. So we have the down state, the init state, the two-way state. So down in the down, no hello packets have been received. In the attempt, which would be right here, the neighbors got to be configured. The neighbors must be configured manually. It applies only to non-broadcast multi-access. Non-broadcast multi-access is going to be think frame relay when you're talking about those. The init state, hello packets are received from another router, but still has the absence of the router ID. The router IDs are important here. That's how it keeps track of things. For the receiving router in the neighbor field, it indicates that bidirectional communication hasn't been established yet. Two-way, the hello packets include their own router ID. That means that, hey, it heard me and it sent this back to me. That's when you hear your own router ID. In the neighbor field, have been received, so we have bidirectional communication at that point. So then we have the X start and the exchange state. These are other things, the LSA acknowledge message and the link state update. I need info on the new network, and then the link state response. These are just other ones that exist. Full is what we want to be, is all the LSA information is synchronized among the neighbors. And notice that it is among the neighbors and not between the neighbors. Between would be two. This would be between. Among is when we had all these other guys up here. So they're all sharing information. This is the network that we're going to look at. You notice we have different areas. Yours is not going to be quite this one. We've got area 0, area 1, and area 2. These are the one I want to do the demo on when we do these things. This is the same thing. Some different commands, and again, I think this is a table right out of the book. These are kind of handy commands to have. Show IP OSPF neighbors, tells you who your neighbors are and what's going on with them. The interface displays the OSPF information about an interface. And one of the things, if you're having problems, and when we do the troubleshooting, we're going to have problems, is that if we have a passive, it'll tell you that you have passive. Show IP protocols shows you all of the dynamic protocols that are running on the router. Show IP route verifies the route table, and if we're using IPv6, it's going to show IPv6 route. Show IP OSPF database is going to be the summary of the database, and these are all, look at these things, and they have you do that in the lab, but look at them when you go through these things. And OSPF 3, I just put this up. The difference, big difference, and the other thing you have to do is turn on OSPF v6, just like you do the IGRP, which he doesn't show here. Config T, what you do in these is we have the addresses already on the interface, and the lab that you're going to do already has the IPv6 and IPv4 interfaces, addresses on the interfaces, so you don't have to worry about those. All you have to do is, you don't even have to worry about typing them in because they're a pain to type in my humble opinion. All you have to do is go to the individual interfaces and say IPv6 OSPF area 1, and that's going to be here on the corp router. On these guys, we'd go to the, on New York over here, we'd go to gigabit 01 ISPF, IPv6 OSPF, and 1 is just simply the process ID. That can be any number. It's up to you. You can use 1 on all of them. You can use a different number on all of them. It's kind of probably a good idea to be consistent and use the same one. So what it, again, it's the process number. When we do that, we just go to the different areas. We have to tell it which area that this interface is sitting in, and on corp here, all of them are in area 1. When we go to San Francisco, the serial interport is going to be in area 0. I said area 1. They're all in area 0. This is 0 here, 1 and 2 here. But the serial is going to be in area 0. The other 2 are going to be in area 1. And these guys will give, and when we look at the show IP route, we're going to have what's called inter-area routes, which means that we've got a route going between the different areas, among the different areas. With that, let me pause this, and we'll do a configuration.